You may have noticed that left-hand sums and right-hand sums have some pretty serious issues with overestimating or underestimating an area bounded by a curve. And so what we're going to do to correct for that here is to use what's called a midpoint sum, meaning that we measure the height of each rectangle at the middle of each subinterval. So we're again going to slice into n rectangles. But this time we're measuring height from the center of each subinterval. So we can see the advantage of this approach in the picture, where a little bit of each rectangle is above f of x and a little bit is below. So we have a little bit of overestimate and a little bit of underestimate canceling each other out partially. So generally with a midpoint sum, you get a lot more accurate approximation. All right, now I'm going to label A as x0, B as xn, and these are my cut points for the approximation. So I would have an x1 here, an x2 here, and so on. And somewhere in the middle, I've got an xi. So let's get to work on expressing all this stuff mathematically. I start with getting the interval width, and that's b minus a over n. And then I want to get a general expression for the ith cut point, and that is the starting point plus I steps to the right. Then I need an expression for the height of each rectangle, and this time I'm going to take the time to do the first one explicitly. So the height is measured at the midpoint of the subinterval, which means I need the average of the first cut point x0 and the second cut point x1, and then I'm going to take f of that. So I'm going to have f of x0 plus x1 over 2. And that gives me the height of the rectangle at the midpoint of the subinterval. So I'll say it like this. First rectangle, that's going to have a height of f of x0 plus x1 over 2. And the area of it would be given by that height multiplied by the width. So our area approximation in expanded form is going to look like height of the first rectangle plus the height of the second one, and so on and so on and so on, all the way till I get to the last one. And I can see at the last rectangle, I'm going to measure the height halfway between xn minus 1 and xn. So I'm going to have f of xn minus 1 plus xn, all divided by 2, and a width of delta x. And now I can put this into summation notation. And I'm going to do this as I goes from 1 to n. And my first rectangle, well, it has an x0 in it. So if I'm plugging in I equals 1, that means my subscript here must be an xi minus 1, so that when I substitute I equals 1, I get x0 for that first one. My second cut point for that rectangle is I1. And again, I'm averaging those so that I can measure the height at the center of the subinterval. And a final check that our summation notation makes sense is to plug in the upper limit for I, which is n, and that would give me f of x n minus 1 plus xn, and that's what I see here for my final rectangle. So my notation is working. And now I have a general expression for a midpoint sum, and I'll just call that MPS. Let's apply our midpoint sum formula to this simple function, e to the negative x squared. I'm trying to approximate the area on the interval 0 to 1, and I'm going to slice into n rectangles, measuring the height of each one at the center of each subinterval. So my midpoint sum looks something like this. Again, the advantage is if I just pick out this rectangle right here, the advantage is that that rectangle underestimates on the left side but overestimates on the right side. And that underestimate and overestimate partially cancel each other out. So these approximations converge on the answer much faster than left and right sums do. Okay, I'm going to start out by labeling my starting point as x0. My finishing point would be x10 because n is equal to 10. That means this cut point is x1, this is x2, and so on and so on. And I'm going to get an expression for the interval width. I should say the subinterval width, and that's the interval width divided by how many rectangles I sliced into, and that's 1/10. Then I need an expression for the ith cut point, and that's just the starting point plus I steps to the right. Or I could call that I over 10. And then if I just briefly write out my area in expanded form, this helps me to check my summation notation. The height of the first rectangle is the value of f at the midpoint of the subinterval. And that's true for the rest of them as well. So my first height is going to be f of x0 plus x1 over 2. That's halfway through the subinterval times delta x. I will have all the ones in between, and then I want an expression for the final rectangle, which will be f of x9 plus x10 divided by 2 times the width of that rectangle. Placing it in summation notation, I have the sum as I goes from 1 to 10 because I have 10 rectangles. And then I just need to make sure I'm careful with these indices to make my approximation start and finish in the right spot. So I'm going to have xi minus 1 plus xi divided by 2 delta x. Just check that it works. When I plug in I equals 1, I get x0 plus x1 over 2, and that's my first rectangle. When I plug in I equals 10, I get x9 plus x10 divided by 2, and that's the height of my last rectangle. Just showing it in the picture real quick, it looks like that. Now we can actually plug this in to our function that we were given. And I have the sum as I goes from 1 to 10, f of xi minus 1 plus xi over 2. Okay, so my function f is e. So I have e to the negative. When I evaluate it at this argument, I'm going to get xi minus 1, which is I minus 1 over 10, plus xi, which is I over 10, added together, all divided by 2, and then squared, and then I have a delta x over here, which is a 1 over 10. Now this can be cleaned up a little bit before we go to a computer algebra system. If I add these two fractions in here, I get 2i minus 1 over 10. If I divide by 2, I get 2i minus 1 over 20. So I'm going to have the sum as I goes from 1 to 10. I guess I'll just put the 1/10 out in front. And then I have an e to the negative 2i minus 1 over 20 all squared, and I've got my midpoint approximation set up. Here we are in maxima, and I've put the sum in here as the sum of 0.1, so that's the 1/10, times percent %e, that's the special symbol for e in maxima, to this power, so negative quantity 2i minus 1 over 20 all squared. And then we summed it up as I goes from 1 to 10. So I'm going to hit Shift Enter and get a decimal approximation. And I get 0.747 on this. Now I want to check against Maxima's built-in numerical integration algorithms. So I've set up the quad QAG function in Maxima. I have my function e to the negative x squared. I'm integrating as x goes from 0 to 1. And then I put in a last number here. And this is just my choice of which numerical integration algorithm to use. You can put in any number from 1 through 6, and they all work great for our purposes. I hit Shift Enter, and I get the first number here is my area approximation. The second number, by the way, is an estimate of how much error is being committed, so I can see that's happening in like the 15th decimal place. So these are extremely precise. And I get 0.7468, or if I round to the thousandths place, 0.747. So this turned out to be a great idea to have these underestimates and overestimates canceling each other out partially on each subinterval, and we get a way more accurate result. Even with just 10 rectangles, we were accurate to the thousandths place.